problem. Ben, I'm going to make sure you see this. And I'm just going to give you a couple minutes, and then we're going to do it. Okay, and so we're just going to do the next 20 or 30 minutes where it's simply doing some review. And again, in a normal year, I would have done this way more. It's just with our sake of time, we're just trying to get through as much as we can. So here we go. Whoops, that is not what I wanted. Ben, can you see that?
Yep.
Man, I don't think we can see it. How do I get rid of the top? Just a second here. I got it. We can't see it in the room. I'm just going to write at the top. So this is what it says at the top. So it says this: at 40 degrees Celsius, KW, it changes. KW is 2.92 times 10 to the negative 14. Okay, knowing that, that's what's on the top. Calculate the H plus, the OH, and pure water. Try this. Okay, we'll go ahead and do this. Bless you. Now the key formula here is this. And this is at 25 degrees Celsius, and that is, I think, the one you're going to use on the test. Okay, but here, the temperature went up, the K value went up, so this must be an endothermic reaction. So we know that Kw equals H plus times OH. Well, in this case, because the K value has changed, it's going to be 2.92 times 10 to the negative 14th equals H plus times OH. Well, if it's a neutral solution, it's pure water, these two would be equal. So they're X times X, which is X squared. So what I'm going to do is I'm going to take the square root of that. So if I take the square root of that, it gives me to 3 sig figs 1.71 times 10 to the negative 7. So this would be the H plus, because it's pure water, it doesn't have more of one than the other. Okay, then number 2, pH, and again, on the formula sheet, it tells us this is actually how I do it on my calculator. I do the negative log of the H plus. I'm going to do the negative log of 1.71 times 10 to the negative 7. So if I do that, so I go negative log 1.71 times 10 to the negative 7. And remember, watch sig figs. When you do a logarithm, so the pH and the POH is the sig figs start at the decimal. So I want 3 sig figs here. So I have 6.767. Again, 3 sig figs. Just watching your sig figs. Okay, and then number 3. So now I'm going to be using this equation, or actually this equation right here. So I'm going to be using 2.92 times 10 to the negative 14 equals H plus times OH. This time we are told that the hydroxide, remember that's the hydroxide, is 0.100. So I'm going to plug that in here. 0.100. So this is X. And if I can solve for X, I will solve for H plus, and then I can find the pH. So if I solve for X, what I get for X is 2.92 times 10 to the negative 13, and then I'll do the negative log of that. So if I do the negative log of 2.92 times 10 to the negative 13, and watch my sig figs, I want 3 of them. I get 12, so the pH, I get 12.535. It makes sense because it's a basic solution. Okay, but the reason I wanted to do this problem is, again, the KW equation, the pH, the POH, and then H plus and OH, how those work. Questions? You okay with that? Ben, are you okay there at home?
Yep.
Okay. You can see the board good enough?
Yeah.
Hopefully so. Okay. On to the next one. Can you see that one, Ben?
Yep.
Okay, there you go. Try that one. Okay, so the key thing on this problem is to recognize this is a strong acid. And one thing that's always a clue is when they don't give you the K value. They don't give you the K value, it's probably a strong acid or a strong base. And again, you guys really don't have to do this, but I'm going to do it just to be consistent. Is I'm going to always write out the equation. I'm going to set up the ice table. And if I start with 0.020 here, and because it's a strong acid, what I start with is completely gone. Oops, should have been 0. I'm going to end up with 0. Okay, so then the pH is the negative log of the H plus, so it's negative log of 0.020. So if I do that, the negative log of 0.02 comes out to be 2 sig figs 1.70. Anybody else get this? We good?
Wouldn't it be 1 point? Oh wait, no, I just did sig figs wrong.
2 sig figs.
Wait, I thought the sig figs started after this.
Right, and so this 0 would be significant. Because this number has, that 0 is not significant. This is a good question, Al. Okay, we all right? Okay, so the next one, I'm just going to write on the board. Now I'm going to keep going on. Okay, so. Okay, here we go. Next one. Ben, can you see that?
Yep.
You know, an acetic acid here, guys, if you don't know the formula of the acid, just always go HA, kind of the acid, and then this is a monoprotic acid. Usually means it's going to give off 1H. So you really don't need the formula for the acid. Okay, go ahead and try that one. You know, write the equation. Definitely big thing on the test is doing these problems. I would write the equation. And then I do an ice table. And again, if it's and that's why even with strong acid, strong base, I do that. Yeah, sure.
I know that's not on this, but when you're checking for the first X to see if it's a significant number, what's the number you're looking to be above?
100.
100.
Around 100 or above.
100 or above.
And actually, they asked me yesterday, it was a good question. One of them asked Juliana, I think, you don't have to do that on this test. You could, it's good what you're thinking, and especially when it comes to the AP test. I'm going to tell you, on our test, and I'm thinking the AP test, we'll always disregard it. So if you don't show me the work in doing that, it's okay. But it's a good idea to do that, really. So Jordan, if I took 0.1 divided by 1.8 times 10 to the negative fifth, that's like, what, 1,000 or 10,000? It's like way over 100. The number you're looking for there is those 100. Okay?
Mr. Wood?
Yes.
Is there any time, like on the AP exam, that we'll have to do that rule?
I don't think you'll even have to show it on the AP exam. I think it's pretty much going to be, but it's not a bad idea though, I think, because I bet at some point you definitely will have to do it. But if you put that as part of your work and you just say, okay, I'm going to ignore X because of this. And then at the end, go back and show the 5% rule. I'm not going to hold you to do it on this test, but if I'm grading that, and again, the way they do grading, I don't know if I told you this, but they gather a bunch of AP chemistry teachers for it's like 8 days, and they sit and they literally for 8 hours a day they grade the same problem. And so you can only imagine how monotonous that is. I'm not going to be doing that. I'm going to be fishing or golfing or hiking or something. But I think, Rex, if you do that, and another thing too, Miss Riddle told me this, and she was at an AP conference, and I think it's the right thing to do. On our test, I really like it if you can circle the right answer, but on the AP test, don't circle an answer. Don't circle an answer. So we're just trying to get every point every way we can. And if you circle an answer, then the graders think, oh, that's the answer. Now, I would try and show your work all the way out to like your final answer, but if somewhere in there you had the right answer leading up to that, if you haven't circled it, I think you've given yourself a chance for more points. Does that make sense, Rex?
So for anything with chapter 12 or 13, should we do that rule?
I would. If it's an equilibrium problem, I would on the AP test. Just say, I'm going to ignore X because of this. And then at the end go, okay, now I'm going to check it. 5% rule was an okay assumption. I think it's a good idea. Okay, so here's my reaction. This one's a weak acid, so it's this. So again, writing equations, ice table. So we have 0.100. You guys are asking great questions. Minus X plus X plus X. So what Jordan and Rex are saying is if you go back, and that was very encouraging, your guys' question, but if I take the initial concentration divided by the K value, if that's 100 or greater, ignore this X. This is way greater than 100. So I can ignore the X. So I take the Ka 1.8 times 10 to the negative fifth is equal to X squared over 0.100. So if I solve for X, so 1.8 times 10 to the negative fifth times 0.1, take the square root of that. So what I get then for X, which is the H plus, is 0.0013. And then I'll do the negative log of that. I get 2.89. Anybody else get this? Nobody else got it? You got it, Carson? If Carson got it, then I feel like I'm doing okay. Okay. Questions on that? Okay. Now, the next one I'm just going to write on the board here. Okay, so what I want you to do here, so I'm just going to do this. Okay, all I want you to do here, so let me write this on the board, is I want you to identify these as acidic, basic, or neutral. So identify these salts as an acid, a base, or neutral. So here they are. So number 1 is BAF2, acid, base, or neutral. Number 2, NH4Cl. Number 3, this big old monster, CH3, NH3Br. Number 4, KNO3. Okay, those, each one of those, acid, base, or neutral. Is that South Dakota Mines, the Hard Rockers?
Yeah.
I like that. Cool. Are we good? No response. Okay, so here again, what I look at, and this is where I got to remember the list of strong acids, strong bases. Barium came from barium hydroxide. It's a weak link, so it's not going to be able to hydrolyze water. But F would have come from HF. So this is a stronger conjugate base. This solution would be basic.
Should we memorize those lists?
You should memorize the list of those 6 strong acids, and there was like 8 or 9 strong bases, yes. Can you name this? Ammonium chloride, right? So ammonium, so I've got ammonium and I got chloride. Well, ammonium is not from that list, but Cl is. It comes from HCl, Lexi, and that's why it's good to know that. It's always acid-based. This solution would have been acidic. Now, the next one's a little bit confusing because there's a lot here. So I tried to identify something I know, and what I know is this. So in this comes from like the problem we just did a few minutes ago. This is from a strong acid, so it's a weak link. So this solution would be acidic as well. And here, K and NO3, K comes from a strong base, so it's a weak link. And NO3 comes from HNO3, it's a weak link. So the best we can say here is acidic. And on the test, there's going to be a section where there's 4 or 5, just exactly like that. Okay, couple more, almost done. Ben, can you see that?
Yep.
Okay.
Would it be okay if after this we did like a couple of those like synthesis problems?
Yeah, we can. We're gonna do. That's actually going to be the last slide. Okay, so here we go. You have to on this one. You have to be given a table, or you have to be given the K values. Okay, remember the larger the K value, the stronger the Ka, the stronger the acid, or the larger the Kb, the stronger the base. Okay, go ahead and take a minute. Try those two. And then the last one we're going to do, Rex, is exactly what you just asked.
What's our correction today?
I haven't looked. It's always hard to see them.
I know. Where is it? 610? So it looks like it's 612. Maybe?
Okay, so the larger the K value, the stronger the acid, if we're talking about Ka. And this is where, like Lexi said, you want to have the list memorized and in your brain. First of all, part of the list here is to recognize, so number one says order the following from the strongest acid to the weakest acid. So you should note the strongest acid here is HNO3. And the dividing line between the strong acids and the weak acids is H3O. So H3O is here. The other acids are weaker acids than H3O. So then if I go to the table, so here's HOCl, and then here is NH4. And we're looking, the higher the K value, the stronger the acid. And again, I always look at the exponent. So hypochlorous acid is -8. Ammonium is -10. So that would mean HOCl is a stronger acid, and then ammonium is weaker acid. Okay, so H3O hydronium is the dividing line. Okay, and then number two is kind of the opposite. Remember, the conjugate base of a weaker acid is a stronger conjugate. So everything here is going to be the opposite. So if I go from the strongest to the weakest, NH3, because it's the conjugate base of a weak acid, it's a stronger conjugate. And the same thing here with this hypochlorite, that would be the next. And then water is the dividing line for the conjugates. So the stronger conjugates are going to be a stronger base in water, and they're going to hydrolyze water. And that's why we can do a problem like we did those couple in class. But the conjugate base of a strong acid is such a weak base that it can't hydrolyze water. We okay? Okay, last one, and this is exactly what you asked for, Rex. So here. Okay, so here we go. So this one's going to take a couple minutes. And then this will be our last review problem. Okay, so if you read this, Ben, can you see that?
Yep.
Okay. So it says write equations for the following reactants. Represent substances in solution as ions if the substances are extensively ionized. What does that mean? It means write the net ionic equation. So if you have a strong electrolyte, which is strong acid, strong base, soluble salt, if you have those, you want to dissociate them and get rid of the spectator ions. The one I told you that we did just a couple days ago in class, if you take a gas and you bubble it through a basic solution, it's going to be a two-step process. And the first reaction is going to be the gas with water. Okay, I'll give you guys a couple minutes. Go ahead and try this. Oh, jeez. I was afraid of that. Oh, well. It's there for testing. So you're not supposed to have it. I don't know quite what.
I didn't know if you got it, but on Friday when I was here, I gave a tissue box.
I think I got it. I think I got it. And I put in, today, guys, I put in both the last test grade and the lab grade. As a matter of fact, I got the lab. I'm going to pass it back to you right now. And Lexi, you should look there. It should be in Infinite Campus, and it should, if it's not reflected right, I think I did get it. Let me know if I didn't do it. I can't wait to see the results.
Oh, yeah, right.
I think that's it.
Yeah.
Yeah, just kind of.
And then I think there was
You did. I know. You're coming tomorrow.
Oh, is it?
Oh, well, that worked really good.
Yeah, I meant
Why?
Why do you get stuck in Utah? Was it weather bad? What? Oh, did it? It's an automotive problems, huh? Yeah, stuff like that. Yeah.
Oh, what is it?
So I put in, and you guys can check this whenever, but I did put in the last test, and a couple of you guys still need to come in and do test corrections. And it should have included those Kleenex boxes, and I also put in this lab, so you guys can keep checking that. Okay, so I'm going to start working on these. Some of these I know could take you a little bit of time, but on the test, on next Tuesday, there will be a section of where there'll be 4 or 5 of just like these. And this is definitely fair game, good stuff for the AP test. Okay, so number 1, sodium hydroxide. Now here's a question. How do you write nitrous acid? How do you write nitrous acid? Nitric acid is HNO3. Remember, atic-itis. So nitrate goes with nitric, and then nitrous with nitrite. So it's HNO2. So this is an acid-base reaction. And remember, acid-base reactions, we always get off a salt. So in this case, it would be the NaNO2. And you always got to check the charge. So +1, -1, those would cancel out. And you always get off water. Okay, so acid-base reaction, you always get off salt and water. And there's one problem here I'm going to do next that's not up here that we need to, that's an acid-base reaction I want to review too. But back to this. So then I balance it. This one I think is actually balanced. It doesn't always happen. I think this one is. So 1 Na, 1 N, 2 H's, 3 O's balanced. Okay, but then, so a strong electrolyte. So what I dissociate are strong acid, strong base, soluble salt. So strong base, I'm going to dissociate, but weak acid, so I'm not. Soluble salt, remember these ions, Na, K, NH4, and NO3. When we see those ions in an ionic compound, they're soluble salts. So here I'm going to dissociate this so I get Na plus OH, separating it into its 2 ions. But a weak acid I'm not going to dissociate because it's not going to dissociate very much. Soluble salt, I'm going to dissociate, so I get Na and nitrite ion. And then I have liquid water. And I'll slow down here, I'm going too fast. Okay, now I will get rid of the spectator ions. In this case, there's only one. One that's the same on the left and the right, that is sodium. So this is the overall reaction. So OH plus HNO2 makes NO2 negative. This should be AQ. Okay, questions there? Okay, before I go to number 2, though, here's the other one that's an acid-base reaction. Let's say that we've got this. We've got Li2CO3 plus HI. Okay, so recognize this. This is something, again, more memorization than normal. We've got an acid plus a compound with CO3 carbonate or bicarbonate. If we see one of those two, it's going to be an acid-base reaction. So again, it's all, what do you always get off an acid base? Well, we always get off a salt. So we have lithium iodide. So the +1, -1 we cancel out. We always get off water. But in this case, you remember what else we get off? Carbon dioxide, CO2. Okay, so when you have an acid with a compound with CO3 or HCO3, I don't think I have one like this up here, you still get off the salt, you still get off water, so we still always in acid base get those off, but we also get off CO2. And then I have to balance, so I need a 2 there, a 2 there. I think that does it. So carbon, carbon, 2 H's, 2 H's, 3 O's balanced. And then I could dissociate from there. But anyways, remember that one too. Okay, number 2. So we take gaseous sulfur trioxide. Hopefully that one's easy to remember. Trioxide like this. So it's a gas plus water. This is one that was new at the end of this chapter 14. So whenever you take a metal or a non-metal oxide, sulfur is a non-metal, plus oxygen, and you combine it with water, you get off an acid. And it's just like a big synthesis reaction. So we get off H2SO4. So 2 H's, 1 S, and 4 O's. And that should be balanced. Then, again, strong electrolytes, strong acid, strong base, soluble salt. Well, what I've got here is this is a strong acid. So it's going to dissociate like this. So if you skip this step and just wrote that in, that would be okay. Or if you wrote it like I did, that would be okay too. No spectator ions in that case. Okay, number 3. So solid potassium oxide. How do you write potassium oxide? K's positive 1, O's negative 2. Got to know the charges. How do you write potassium oxide? K2O, right? And it's a solid, and because it's a solid, technically it's in the category where it would be a soluble salt, but it's a solid. So we're not going to dissociate it. Plus water. So here was another category. This time, if I have a metal oxide, potassium's a metal oxide plus water, we make a basic solution. So what I hear, again, a big synthesis reaction. So K2O2, H2. And then if I look at this, and now familiarity with almost 2 years of chemistry, I would see it be better written like this. Anything here dissociate? Strong acid, strong base, soluble salt? Strong base, right? Strong base. So this is going to dissociate. This is why Lexi's question was a good one. You do have to memorize that list. So like that. Okay, the next one. The next one's going to take a little bit more room. So I'm going to go back up to the top of the page. There's one like number 4 on the test, just like we did in class a couple days ago. So whenever you take a gas and you bubble it through a basic solution, it's going to be a 2-step process. So the CO2 gas, the first thing it's going to do is it's going to react with water. If it's a solution, it's water. And so it's going to be like number 2. We have a non-metal carbon, a non-metal oxide, plus H2O is going to make H2CO3. Okay, not the point of the problem, but you know the name of H2CO3? Carbonic acid. Very good, Alan. Now in step 2, the acid is going to react with the base. Okay, so what's going to happen here, acid base, so we're going to get off H2O, and what's going to be left then is KHCO3. So when you see a gas plus some kind of a basic solution, 2-step process. Okay, now let me balance this. So let's see, potassium is good, carbon is good. One thing here is oxygen, 4, I think maybe good, 2 H's, 3 H's, it's all balanced. Okay, so now I'm going to add these two up. So something common on the left and the right I'm going to get rid of. So I'm going to get rid of this, and I'm going to get rid of this. And so what that leaves me is this. There's actually two ways I think that would be acceptable in this one, and I did it the other way yesterday in period 2. Okay, but now let me just finish this way. Okay, so now strong base, no strong acid, soluble salt, I'm going to dissociate. So I got CO2 gas, strong base, strong base, soluble salt. Get rid of the spectator ions, and so what the overall reaction is this. Okay, now I want to show you how I did this yesterday, and I think both would be acceptable. Questions on that one? If you do it that way, great, you're doing it good. But I think this way would work too. But if you go, I do the same first step. But now I take the H2CO3 and I combine it with KOH, and what I do is this: is I get off H2O plus KCO3, and KCO3 is 1 and -2, so it's K2CO3, and I get off CO2. So here is the acid base where we got, actually I don't need CO2. I've got CO2 is wrong because I've accounted for the carbon, so I didn't need the CO2. So it's just outers and inners. But what I did different here is up here I did HCO3 and here I'm doing CO3, which is okay. Either way to me, if you write it out, would work for our test and the AP test. And then if I balance it, 2 Ks, and now I think I need 2 there. So I think I got 1 C, 2 Ks, 4 H's, 5 O's. Okay, now I add this up. So I get rid of that. I get rid of one of the waters. So what's left over, and I get a different, it ends up to be a little bit different ending. But again, if you show me the steps, to me, the chemistry here works. So then I've got strong base, soluble salt. So if I dissociate those, and then if I get rid of the spectator ions, that's what leave me overall. Either way would work for me. Okay, then number 5, the last one, and then we've done a pretty good review. Hopefully it will be helpful come Tuesday or whenever we do this test. Hopefully we'll do it on Tuesday. Number 5, dinitrogen pentoxide. How do you write dinitrogen pentoxide? N2O5. And it's a gas. And it's mixed with sodium oxide. So again, a little practice here in writing formulas. Sodium +1, oxygen -2, like that. This is where I take N as a nonmetal oxide, plus a metal oxide. What I get off here is, again, another synthesis reaction. And this time I'm going to get a salt. So I get 2 NAs, 2 Ns, 6 Os. So you take a non-metal oxide, a metal oxide together. Remember, a non-metal oxide plus water gives off an acid. A metal oxide plus water gives off a base. And if I combine the two, I get off a salt. Hopefully you will see that this would be like this. Okay, and then this I would technically dissociate This is a solid, so I wouldn't. It'd be like that. Okay, hopefully, was that good to do, or was that okay to do that?
Yeah.
Spend a lot of time with that, but I think it's better than me just giving you problems, and hopefully that is helpful to you. Okay, what I want to do for about 15 minutes then is I do want to start chapter 16. I was really hoping for more time to do that, but I did want to, I just think it was valuable to do that. So here we go, into chapter 16. And again, what I want to do here is I'm going to go through quicker than I normally do, because I want to go over main things. And all you're going to have, Ben, can you see that at home?
No.
You can't. I didn't hit share, my fault.
Actually, yeah, I can. Sorry.
You could see it?
Yeah, sorry.
Oops. Can you see it now?
Yep.
Okay, good. Okay, so I'm going to try and go through stuff here. Because to be honest with you, stuff in chapters 16 and 17 is stuff that I think you can nail. Megan?
Oh, I just have a question. I forget, for like the arrows, when you use like a single arrow versus.
The double arrow should be when you have a weak acid, weak base. Okay? That's a good question too. But what I want to do, and again, I'm going to start today again, 10, 12 minutes, stop. And then I'm going to pick back up with this if everything stays the same on Thursday. And I'm going to spend a good chunk of time Thursday, and then probably half of the Monday after that, and 16. And then I'm going to spend the rest of Monday and then Tuesday and Thursday the following week on 17. And the reason why is I think these are problems that I think you guys can get. Is kind of the way it works in a normal year in our class is that in a normal year, let me just put this up. And again, I'm just going to go through what are the key things that you should get out of this slide. But in a normal year, and like I said, Rex, and he was right. We were talking during Access. He said the second half of chapter 14 got pretty tricky, and he's right. And then what happens, then we go into 15. And to be honest with you, of all the stuff we learn, we always kind of hit, it's like the going over the mountains in Colorado, the peak, the hardest stuff to me is in chapter 15. What we do in 15 is we combine really chapter 13, the equilibrium stuff, with chapter 14, the acid-base stuff. And again, probably not next week, but the following week, and maybe next week, I'm going to post maybe a few lessons from 15 for those that want to watch it. You're not going to be any quiz or any test on it. You know, part of this we're just trying to do as well as we can. But then, typically in early April, we get into chapter 16 and 17. And what happens is the difficulty all of a sudden, not that anything we do is easy. Nothing we do in here is easy. But the difficulty gets much easier. And so because of that, I want to spend, instead of wrestling with chapter 15 and the difficulty that it is, I really think chapter 16 and 17 are going to be represented on the AP test. And when you look at the Princeton Review, you're going to see that. So hopefully this will be beneficial. Okay. So all you're going to have in 16, and I'll give this to you if everything, the schedule goes as is planned, is next Thursday I'll give you the quiz. So some of the main ideas in chapter 16. So kind of the key thing off this slide right here is kind of the difference here, but right here, the bottom of the page. So going back kind of to chapters 12 and 13 is in chapter 12 was about kinetics. Okay, and kinetics is concerned with how fast reactions go. And that's where we took data. We had concentration versus time data, concentration versus rate data, and we determined the order of the reaction. Is it first order, zero order, first order, second order? We had the rate constant, we had the activation energy diagrams, all that. What we did in chapter 13 then was we had the double arrows, like Megan just asked about. And we said, okay, does this reaction go far to the right or far to the left, or does it lie in the middle? Well, what thermodynamics is about, this chapter, and if you have an older sibling or a relative or a parent or somebody that majored in chemistry in college or physics, they may have taken a whole semester in thermodynamics. So we're going to really cover just the basics. But I think if we do this, we're going to be good. But what thermodynamics is about the spontaneity of a reaction. Okay, what that means is spontaneous means it just happens without plan. Now, I'm going to take my mask down for a second. So forever, for as long as I've known chemistry, which is a long time now, we've always used the term spontaneous or non-spontaneous. But now on the AP test, they don't use that. And I can't remember their reasoning. But what they're going to say, and you should note this, I'm going to say this a couple times. They're not going to say spontaneous. They're going to say thermodynamically favorable. So a reaction, so this chapter is going to be all about, again, to me it makes sense, is a reaction spontaneous or not? We're not talking about kinetics. We're not saying how fast it goes. We're not going to say, it will be a little bit about lying left or right. I'll talk about that. And actually what we'll get to when we're wrapping up this chapter is we're going to connect. The key thing in this chapter is going to be this thing called delta G. And I want to just talk about that briefly today. But we will connect delta G to K, to the equilibrium constant that we did in chapter 13 with this thing called the Ratlink equation. Ratlink, that sounds like something interesting. It's just going to be more math. But a spontaneous reaction, what they're going to call it on the AP test is thermodynamically favorable, which means a reaction is going to go right. All those mean the same thing. And so kind of, again, just making main points. So if a reaction is spontaneous, which means it's just going to happen. Now, we're not saying how fast it's going to happen, but it's just going to happen. It means the same thing as what the AP test is going to call thermodynamically, hopefully I spelled that right, favorable. That's what they're going to say. It means the reaction is going to go to the right. And this thing called delta G, which we're going to come to hopefully next Thursday, is negative. The delta G value is negative. So then if a reaction is non-spontaneous, which means it's not going to happen without something going in, then it is not thermodynamically favorable. Which means the reaction would go to the left. So it is going to be related to equilibrium. And the delta G value will be positive. And so again, the key thing really in this chapter is going to be this idea of spontaneous or non-spontaneous, thermodynamically favorable or not thermodynamically favorable. Okay, real quick, just I want to go through these. You don't need to write these down, but here are some reactions that are spontaneous or not spontaneous. And some of these, and I don't think I showed you, but it's always a cool reaction. If you take an alkali metal plus water, it's very reactive, so it'd be spontaneous. If we take a strong acid and we put it in water, it's spontaneous. It's just going to happen. It's just going to dissociate. It's going to happen. But if we put a weak acid in water, it'd be non-spontaneous because it's going to go back more to the left. There, Megan, I should have had a double arrow. And then another factor that's going to play in here, so if I have H2O solid, ice, to H2O liquid, it'll be spontaneous above zero, above zero. But if I take H2O solid and H2O liquid below zero, it'd be non-spontaneous. So the factors that this delta G, which again, I'm going to come to this more, hopefully a week from tomorrow. So then I've got, so what determines whether a reaction will be spontaneous? Well, really it's going to be this delta G. Okay, if it's negative, it's going to be spontaneous, which means the reaction is just going to occur. If it's positive, it will not be spontaneous. Okay, so here are the factors. Number one thing, what's going to depend on, it's going to depend on temperature. Okay, another thing is going to depend on, again, I'm going through this, but the key thing here is right here. Many reactions are exothermic but not spontaneous. Usually, another thing that's going to depend on is delta H. And this is why if we go way back into the fall, so around a little bit before Thanksgiving time, between Thanksgiving and Halloween and Thanksgiving, we did chapter 6, which was thermochemistry, a whole bunch of delta H stuff. Now we're doing thermodynamics. So we're going to do a little review of some delta H stuff. But typically what this slide is showing is usually when delta H is negative, which is exothermic, usually that's spontaneous, but not always. And that's what I tried to say here. So when we have, like here, exothermic reactions decrease the energy of the system, which is favorable. This is the reaction we light a Bunsen burner. It's exothermic. But here, if I take ice and I melt it, it's endothermic, but it's spontaneous depending upon the temperature. Here, ammonium nitrate, which is endothermic, is spontaneous, the dissociation of ammonium nitrate. So usually, when delta H is negative, it's usually spontaneous, but not always. So the second thermodynamic property used to predict spontaneity of directions is called entropy. And actually, it's the third thing. And the letter they use for entropy is an S. And the second law of thermodynamics, which I'm going to talk about again, hopefully a week from Thursday, is about disorder. And it says that all systems move towards a state of maximum disorder. And I always think of the inside of my dresser drawers or the inside of my notebook or my desktop. The disorder always increases as we go. And so that is a good place to stop. So what systems want to do, final thing, is they want to go towards a state of maximum disorder. So usually what states want to move towards when they're spontaneous is they want to move toward less energy, negative delta H, and they want to have more disorder. Okay, good place to stop. Okay, the labs, I'm done. So you have about 10 minutes. If you, again, need more time and you're not ready, you can give me the lab. I'll be here access tomorrow. I'm done talking. Thank you very much. Ben, I am done. So unless you have, did that help at all? Just a second here. Ben, I tried to respond to your email. I don't know if that was helpful or not at all.